Hi, my name is Annabelle Polk. This is part 2 of Project 3 for Dr. Ozbay, simulating a combined Couette-Poiseuille flow. Previously stated, from our ANSYS theory, I found that our max velocity was 7.455 meters per second at approximately 1.2 millimeters on the y. And then we found that our dpdx, our pressure gradient, was 237.4 pascals per meter. We're going to be keeping the same length and height values for our theory, for our worked theory, as well as using 2D, viscous, steady, laminar, and incompressible assumptions. From these assumptions, we can assume that our velocity in our y is going to be 0. Our del u del x will also be 0 from the continuity equation, as well as our del t equals 0 from steady. Another few things to keep in mind is that del P del X, our pressure gradient in a Couette flow, is actually 0, and del P del X is greater than 0 for the combined flow. Just something to keep in mind. We'll start by using the Navier-Stokes equation, and we're going to double integrate it so that we can get this uy function. This will be our velocity flow function. To get this C1, C2, we can use our boundary conditions that were given to us. When y is equal to 0, we know that our velocity should be in the -2 direction, and when y is equal to h, we know that our velocity is going to be 3 meters per second in the positive direction. Plugging in our y is equal to 0, we can find that our C2 is going to be equal to -2. Plugging in C2 and that our y at h is equal to 3, we can find that our C1 is a little bit more complicated, and it's going to come out to 5 over h minus 1 over 2 mu pressure gradient times h. If we go ahead and multiply this by y, we can just plug it into our C1h itself. And then we can get that our velocity flow function is going to be 1 over 2 mu dp dx y squared plus 5 over hy minus 1 over 2 mu dp dx hy minus 2. Just simplifying it a little bit to make it easier to solve for our u infinity. This u infinity is actually going to be our velocity inlet, which was 5 meters per second, which we'll plug in later. First, we're going to plug in our uy that we found into this integral, and just doing some simple integration and plug in for 0 and h. We can continue to find our u infinity. Plugging in u infinity is 5. We can solve for dp dx. Our mu that we also will be using is 1.8 e to the -5. Plugging this in, we can finally solve for dpdx, and we see that our pressure gradient solved through theory is 268.357 pascals per meter, as compared to when we solved it through ANSYS, which was 237.4 pascals per meter. This is going to give us roughly a 10.5% error.